as I was just saying while they were queuing things up for this segment, those problems we just did may not seem that simple, but compared to they are simple relative to what we're going to look at right now. So let's look at solving some slightly more complicated types of equations, and I want to just review a little something with you first. Let's say I gave you x squared, let's keep it real simple, plus 6x. No, let me change it. Let's say I gave you this equation. You would identify this as a quadratic equation. And actually, I'm going to change it again. Okay? Just because I want to make sure that you don't screw something up. Still the same equation. I'm just putting that 12 on the other side. Okay? Because what is a classic mistake people will try to do with this thing? What the classic mistake people will make, and I've even seen calculus students try this, is they'll factor out an x here and have x plus 1 left, and they'll say x times x plus 1 equals 12, and then they'll say x equals 12 and x plus 1 equals 12, and you're trying to invent algebra that is pure garbage. Don't do that, okay? When you see a quadratic equation, the technique you have to do is, first of all, identify it as a quadratic equation, kick everything over to one side, usually in descending order, and then solve that equation using the techniques that you've learned. This particular simple equation will factor, and you all should be just on automatic on that. X plus 4, x minus 3, and so you solve then. The reason this rule or the technique works is because it's called the principle of zero products. If you have items multiplied together equaling 0, this is intermediate algebra, then it doesn't matter. If this item is 0, this statement would be true, or if that item was 0, this whole statement would still be 0. That's the principle. So then x plus 4 equals 0, continuing to solve, x equals negative 4. And over here, similarly, x minus 3 equals 0, x equals 3. So you get this solution or this solution. And then, of course, you always want to go back and check those. Very basic review, intermediate algebra. Watch this. You know that I could think of this equation as x squared equals negative x plus 12. Why not get a graphical perspective of this solution from that? You know what the graph of x squared looks like. Looks like that. And you know what a linear function minus x plus 12 looks like. It's up here with an intercept at 12 and a slope of negative 1. Right? Here are your answers, folks. Negative 4 right here and 3 right there. It's the intersection of where this y value of x squared's value is equal to the linear function's value. The y values are the same here. Okay? So you can get a perspective of the fact that you're going to have a negative answer and a positive answer to this quadratic equation. But this is not an algebra class. This is a trig class. So if I get solutions that happen to be negative 4 and 3, this problem could be, it couldn't be a sine or cosine in here, could it? For any real answers. Because a sine, if this is a sine of an angle or a cosine of an angle for x, what we represent x as, then you know that those trig ratios have to be trapped between negative 1 and 1, okay? So you'd have to use some other trig function in this problem to make this one of these more complicated trig problems, such as secant, or maybe cosecant. Right? Let's use secant. Okay? So let's come back up here and look at the algebra structure. That's what you want to identify, is look at the algebra structure that exists. So if we have a secant of angle theta squared plus secant theta equals 12, and you're asked to solve this, where theta is on the domain from, let's stick with theta in a domain from 0 degrees to 360 degrees. What you need to do when you see an equation like this is realize that it's a quadratic structure, and we're going to set it up as secant squared theta plus secant theta minus 12 equals 0. We are going to factor it. And finish this off and get secant theta equals -4. And over here, secant theta equals 3. Not so bad if you see the quadratic structure, is it? Okay. And now you're back to trigonometry. And right here, the cosine of theta is -1/4. Oh, I'll be darned. We just did that problem in the last segment, didn't we? I like that. So the answers to this, you can go back, rewind the DVD if you need to, okay? Or go back and look at the previous segment. The answers to this, there's two answers in here. One of them is 104.5 degrees, approximately. And the other answer in here is 255.5 degrees. Or we've got to come over here and solve this problem as well. So here, the cosine of theta is 1/3. I'll show you another visual way now of seeing this. Think of your unit circle. Think of your unit circle. You know that your cosine readings are your x readings, aren't they? Your x readings. And one is out here, and 1/3 is about right there. Which means that you're going to have an angle that's up here, right? And 1/3 is smaller than a half, isn't it? Yes, okay. We're good with fractions. 1/3 is smaller than a half, and so normally at a half, you'd be at what angle?
60 degrees.
You'd be at 60 degrees. So do you see that 1/3 here should yield a degree measure answer for theta here a little bigger than 60 degrees?
Yeah.
Greater than 60 degrees for this answer. But isn't there another answer between 0 around to 360 degrees, another answer showing up down here? And if you were again at a half on your unit circle, you'd be down here at, well, how many degrees? 300 degrees. And so we'd expect this answer right here to be a little less than 300 degrees. And that's going to capture two answers that happen to lie for this solution right here within that range of values, that domain of values. So we're going to take our calculator and we're going to punch this inverse cosine of 1/3, and we're going to get an approximate answer there. And that's going to be a third answer. Notice how I labeled it, theta sub 3. And we're going to pick up a fourth answer that would be equal to, how could I get it pretty precisely? What would I have to do? Look at the geometry. I could go to 360, couldn't I?
Yeah.
And back off this value. 360 degrees, and back off that inverse cosine of 1/3 reading. you can, if you're in degree mode, you can punch this, and we'll pick up those answers. Very similar to what we did previously. There's the two answers from before. And then we're then going to take and do this inverse cosine of 1/3. And watch this. I'm going to use 3's reciprocal instead of punching 1 divided by 3 there. There's that answer. And then I'm going to punch 360, and I'm subtract from it that inverse cosine of 3's reciprocal. So there's all 4 answers displayed on the calculator screen. 70.5 degrees. And finally, what's that other one? What did it say?
289.5.
389?
289.
Oh yeah, 289.5 degrees. Okay.
Do you always use 2 pi and subtract it from the inverse cosine
No.
to get the second answer? You use whatever the period is? Because
Yeah,
in this case the period's 2 pi.
Well, you've got to think. You've got to either think of where you all know that an inverse trig function is a function, and you're only going to get one output value there. What you need to be aware of is that in trigonometry there's multiple answers that occur periodically, right? Always. And so what you've got to do then is you've got to have your mental hat on and think your way into what you're dealing with. And
Well, on the other one we did -1/4, the cosine, the inverse cosine of -1/4, right? How come we didn't subtract it from pi on the other side then using 2 pi? It's on the other
well,
side
that
of
was
the
the other
circle.
problem I did previously over here. And I showed you another way of seeing it from the inverse cosine function. I showed you this.
Yeah.
And I also showed you the secant way that you can see it. Also, in the fact of where those answers lie graphically.
Oh, okay, because I see what.
Yeah,
never
and then
mind.
what I did deliberately, back over here just now was showing you another way of seeing it by using your unit circle knowledge. So in mathematics, sometimes people get nervous in math when you're using math because you think there's only one way to get to an answer. And I joke around oftentimes about what's happening when you're out hiking in the woods. You know, if you're standing right up against a tree, you can have a hard time telling where you are. So sometimes you got to step back, step around, take a little hike, come over to a cliff. Do you jump off the cliff? Not unless you got some kind of parasail or something, right? Usually you're going to back up and look for another path down. And there's usually multiple ways to get to where you want to go. Same thing happens in math, applying math. Let's do another style of equation, okay? Instead of a quadratic. So watch out for these. They show up frequently in textbooks. I'll take one right out of the book. Let's find something of a slightly different style. Here's one that looks kind of exciting. How about this? It appears simple, but let's see what it does to us. It says cosine of theta plus the sine of theta equals 0. Cosine theta plus sine theta equals 0. And they want us to solve for all answers on 0 to 2 pi. Will you be comfortable if we go in radian mode like they ask us to here? 0 to 2 pi for our solution set? Okay. What would I probably suggest that you do first?
Graph.
Excuse me?
Graph.
Graph it. Adding sine and cosine together and graphing it might be a little puzzling to us, right? What might be an easier approach? Oh, put it on your calculator. No, let's say your batteries are dead, okay?
Answer.
What about putting one on one side and one on the other side? Okay. So why don't I leave the cosine here and subtract sine theta from both sides? And think of this graphically like I showed you that quadratic equation a little while ago. Draw a graph of cosine. And we want to draw it from 0 to 2 pi, don't we? So here's your cosine graph drawn, 0 to 2 pi. Not including the end point, but including the beginning point, because of the restricted domain for our solution set. Okay? Draw, overlay an upside down sine graph. Overlay an upside down sine graph. Let's see, an upside down sine graph normally has a crest at pi over 2. It's going to have a trough at pi over 2. It's going to have a node at pi. And then it's going to end up with a crest at 3 pi over 2. And then it's going to drop back to its 0, right? So here's your upside down sine graph. Here's your cosine graph. Where are the answers?
Wherever those curves line up, pi over 2, pi, and 3 pi over 2 are zeros.
Right here? Here? Here?
No.
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 It's where the output values are the same. I think that's what you were meaning, Raphael. Right here? Right here, this value is one answer. And it looks like there's another one over here for another answer. I'll label them theta 2 and theta 1. So, because you know there is some symmetry characteristics on these sine and cosine functions, then what are you going to predict this answer to theta 1 to be?
Between 90 and 180 degrees.
And, can you be more precise?
45.
45 degrees more than 90, right?
Yeah.
Equivalent to 3/4 pi. 3/4 of pi. And similarly over here, pi over 4, 45 degrees before you get to 360 degrees. So normally I would think of that as 8 pi over 4 and back off pi over 4 to give me an answer of 7 pi over 4 for my prediction. All right? But that's a graphical solution, which is a very good thing to know. And we probably nailed the answers. Didn't it appear because of symmetry on the shapes and so forth? We nailed it. But we want to be able to do analytical trigonometry. So here's our equation that started out cosine theta plus sine theta equals 0. Seemed real simple. Any idea what to do? Usually when you have a mix of trig functions, remember this, when you have a mix of trig functions in an equation, your objective to be able to solve the darn thing is usually to write it in terms of one trig function. You want a hint?
Inverse one?
Well, can't do it. You know, I can do an inverse cosine of both sides, but boy, the left side I'd like. Inverse cosine of cosine is going to be just theta. That's easy. How about the inverse cosine of the negative sine of theta? That doesn't sound too good. Okay. Any suggestions? What if you divided both sides by cosine theta? If you divide by cosine theta here, this turns to 1. If you divide by cosine theta here, negative tangent, isn't it? Ah, there we go. Cosine theta over cosine theta. This is like standing with your nose up against the tree right here, right? And you're lost in the woods. And you step back and you look at this and you go, oh, I finally see where I've got to go. Okay? Divide both sides by cosine theta. And so and you have an identity that tells you that the sine of theta over cosine theta is tangent. So we have the negative tangent of theta equals 1. And so let's keep on going. Actually, I'd isolate the tangent first. I'd write it as the tangent of theta is equal to negative 1, and now apply the inverse tangent process. But again, be aware, very important, that we want answers that exist in this entire domain from 0 to 2 pi, and our graphical solution earlier indicates that there should be 2 answers. So I'm thinking about my tangent function, and so I could, actually, easy way to do it would be unit circle, and you know tangent is sitting, there you go. It's right there. And your inverse tangent reading is going to come back with this answer right here. Inverse tangent of negative 1 is going to come back with this 7 pi 315 degrees, or equivalent 7 pi over 4. That's what that inverse tangent reading, when you do this calculation, will give you. And then what you need to do, oh, excuse me, I'm sorry. I almost blew it. What's the calculator going to come back and tell you? If you're in degree mode, like we were in the previous problem, it comes back, let me help you. Remember your inverse tangent graph? Goes as high as 90 degrees, as low as minus 90 degrees. And we're at negative 1 here. It's going to come back with negative 45 degrees here. I even had my arrow right. I wrote it as a big positive angle, though, 315, right? See, the calculator is going to come back with minus 45 degrees there, or your brain will come back with that if you remember this, or it will come back with negative pi over 4. With me? But those answers are no good given the original restriction on the theta. So we have to make sure these answers come back only between 0 to 2 pi, positive. 0 to 2 pi. So what we're going to have to do is we could add 360 to this, or 2 pi, okay? So our answers here are going to have to be plus 2 pi, or we could take this negative answer and add to it pi, couldn't we? If we add pi, this is going to give us the second answer right here. And the first answer is going to come by taking that inverse tangent of negative 1 and adding pi to it. So you have to, usually you have to have some graphical perspective to be able to sort of see these parts. And you're going to end up getting your final answers coming out of here of, this one's going to be 7 pi over 4 for an exact answer. And I believe they probably wanted an exact answer here. And this one's going to be 3/4 of pi for theta 2 and theta 1. Okay, so let's go ahead and stop this segment now. I've shown you a couple different styles of more complicated equations, and that's kind of similar to what you'll see in your homework. And then what we'll do in the last segment today is focus on applications. Okay? So while they're queuing up,